I think so, yeah.
Okay. Welcome again. It's great pleasure to have our colleague and friend for many years, Professor Davesh Maulik from MIT, who is going to talk about one of his Frontiers of Science awards out of two that he got received this year. And he's going to talk about P equal to W conjecture for GLM. Please.
Right. Thank you for the invitation. Is this microphone working for you guys? Is it too loud? No? All right. If it is, let me know. Okay, so thanks for the introduction. Thanks for the opportunity to speak here. So what I would like to talk about today is what's called the P equals W conjecture, which is a conjecture involving about the subject of non-abelian Hodge theory for curves. Everything I'll be talking about that's kind of my own work is joined with my collaborator, Junliang Shen, who wanted to be here but couldn't make it. So let me begin by just talking about a little bit about non-abelian Hodge theory for curves before talking about what this conjecture says. So first, let me just fix for this talk. C is going to be a curve, usually of genus greater than 2, greater than or equal to 2. And I'm going to go ahead and fix a rank and a degree, which will be coprime. And so the non-abelian Hodge correspondence, at least the version I'm going to use, involves two different moduli spaces associated to this curve. So the first moduli space is what's called the moduli space of Higgs bundles, which is some kind of algebraic moduli space of some kind of algebraic gadgets associated to the curve. It'll be parametrizing what are called Higgs bundles, which consists of two pieces of data. The first is going to be a vector bundle E of rank R and degree D. And the second is this theta is what's called a Higgs field. It's going to be an endomorphism of E twisted by the canonical bundle of the curve. Okay. So it's two pieces. A Higgs bundle consists of two pieces of data, E and theta. And to get a reasonable moduli space, I'm going to impose a stability condition. So I'm going to look at what are called stable Higgs bundles. And I won't write down the definition of stability, but if you're familiar with stable bundles for a curve, it's the same definition involving the slope, the ratio of the degree to the rank, except I'm only going to consider subbundles that are preserved by this twisted endomorphism. Okay. So the way you should think about this Higgs field, so okay, vector bundles maybe we're okay with. The way to think about this Higgs field is that, okay, so theta is an element of Hom from E to E tensor K. And then by Serre duality, you can think of this Hom as dual to x1 of E comma E. And this x1 is the tangent space at E to the moduli space of vector bundles on a curve. So you should think of this as a cotangent vector. At this point in the moduli space of bundles. And more generally, you should think of the moduli space of Higgs bundles, if I ignore stability, as something like the kind of total space, the cotangent bundle of the moduli space of bundles. So for instance, if I restrict myself to stable bundles, the moduli space of Higgs bundles contains the cotangent bundle of the moduli stable bundles. And this is like an open, dense subvariety. But it's bigger because you can have Higgs bundles where the underlying bundle is not stable. So this is a strictly larger. But this is still a useful perspective. For instance, there's a natural symplectic form on this cotangent bundle because it's a cotangent bundle. And that extends to a symplectic form on this whole moduli space. So for instance, this moduli space of Higgs bundles is algebraic symplectic. And in fact, it's what's called a hyperkähler. Yeah. Right, so this is moduli space of stable bundles. So yeah, if I did the full stack of bundles, then that would be bigger than the moduli space of stable bundles, yeah. So if I ignore stability, then the stack of all Higgs bundles with this erased is literally just the cotangent stack to the moduli stack of all bundles. Okay. So this is the first moduli space. It's the moduli space of Higgs bundles on the curve. And again, it's parameterizing something, some algebraic or holomorphic data associated to C. The second moduli space is what's going to be called the character variety, or sometimes the twisted character variety associated to C. And it's something that doesn't depend on the algebraic structure of C at all. So what this is going to parameterize is I'm going to fix some points on my curve. And I'm going to just look for representations of pi 1. So this is going to be mapped from the fundamental group of C minus P. So I'm going to puncture my curve at this point P. And just look for homomorphisms to GL R of C. With the property that if I look at the loop around my puncture, that gets sent to a scalar matrix given by a certain primitive rth root of unity, depending on D. Okay. And I want to look at these homomorphisms up to conjugation. Okay, so this is, again, usually called the twisted character variety. Twist because I'm imposing this condition on the puncture. And so the only thing I'll say about this space right now is that this is smooth. Both of these spaces are smooth because of this coprime condition I put here with stability. But this variety is an affine variety. So this is actually an affine variety. And it's not such a mysterious object because this pi 1 is very explicit. So if you really, at least before I take the quotient, you can really just think of this as a bunch of matrices a bunch of invertible complex matrices with the property that the product of their commutators is this scalar matrix. But I still have to then mod out by the GLR action. Okay. So these are my two moduli spaces, this algebraic one and this more topological one. And so then the statement, which is some case of non-abelian Hodge theory. Okay, I won't write the. So this is non-abelian Hodge theory. And this is subject was developed basically in the 80s by many people, but the kind of main names I'll write down are kind of Corlett, Donaldson, Hitchin, and Simpson. Said that these two moduli spaces, the moduli space of Higgs bundles and this character variety, which is are naturally in bijection with each other, and in fact, there's a C infinity diffeomorphism between them. So this is really kind of, this is a theorem of, really some kind of analytic content to it. The way this theorem is proven is that there's some, third space of, what are vector bundles with some kind of special metric on them, like a harmonic metric, and then you specialize to each of these two different spaces in some way and show that each of those specialization maps is in fact a diffeomorphism. But let's see what this correspondence looks like just in the case of R equals 1, where you don't kind of need a huge machine to understand it. So the left-hand side, this moduli space of Higgs bundles. So remember, a Higgs bundle, which I've erased the definition for, is a vector bundle and then this kind of twisted one form. If I'm in rank 1, the vector bundle is just a line bundle. So I'm going to look at, say, maybe I'll call it just degree D line bundles. And that, endomorphism valued one form just is a one form. Okay. That's the left-hand side of this correspondence. The right-hand side of this correspondence, well, again, it's just going to be, you know, one by one invertible matrices, and the product of the commutators needs to be 1. So that's just C star to the 2G. And so then you can just kind of eyeball what this kind of diffeomorphism is going to look like. This is just a complex torus, and this is just a complex vector space. So this is going to be S1 to the 2G cross C to the G. And if I rearrange this, I can kind of regroup things. So this is kind of, you know, S1 cross R to the 2G. And then this S1 cross R you can identify with C star. Okay, so that's how you can think about this diffeomorphism in this example. And already in this case, you see something kind of important, which is that, you know, whatever this diffeomorphism is, it is completely brutal when it comes to the algebraic or even just the complex analytic structure. And that's something that's true in general. So this, I'll put a star here. So star is, you know, badly disrespects the complex analytic structure. And one way of seeing that in general is that, well, the right-hand side, as I said before, is always an affine variety. In particular, it has no positive dimensional compact subvarieties. Of the left-hand side, on the other hand, admits a proper surjective map to some lower dimensional affine space. So D here is just half the dimension. Which is called the Hitchin map. And one way of thinking about what this map is that this affine space is just spec of the ring of global functions. But you can also study it more explicitly if you want. Okay. But I'm not going to do that. But this Hitchin map is going to play a major role in this talk. But for now, let me just point out that in particular implies that these things can't be isomorphic as complex manifolds because I have all these fibers, which are, you know, half-dimensional proper subvarieties of the Higgs moduli space. And one way of thinking about what this map looks like is that it turns out that this, the fibers of this map are Lagrangian with respect to the symplectic form on the Higgs moduli space. So the generic fiber of this is going to be some kind of smooth abelian variety. But then as I kind of, you know, specialize my fiber, I'll pick up kind of complicated singularities. And the fiber over 0 is some kind of, you know, non-reduced, reducible mess. Okay. Are there any questions so far while I gather my notes? So just to summarize, what we have right now is two moduli spaces associated with my curve, this algebraic one and this topological one, and this kind of, you know, transcendental diffeomorphism between them. And so the vague question you can ask whenever you're in this situation is that if I have a kind of diffeomorphism between two algebraic varieties, you can ask, let me keep it on the board, which algebraic structures on one side have some meaning on the other side. So for instance, a question which I will not say anything about because I don't know anything about it, is you could ask which algebraic subvarieties on one side are still algebraic on the other side. And I actually don't know if there's even a good proposal for the answer to that question. So this P equals W conjecture is about a specific example of that question, where I'm going to take something kind of algebraically defined on the character variety and move it over and try to find some interpretation for it on the Higgs moduli space. Okay, let me say what this conjecture is about. So remember, I have this diffeomorphism between these two moduli spaces. And so in particular, if I look at just their singular cohomology, using this diffeomorphism from non-abelian Hodge theory, I can identify their singular cohomology. And now, using the fact that, for instance, the right-hand side is not just some topological space, but an algebraic variety, this cohomology carries some extra structure. And so the particular extra structure that I'm interested in is going to come from mixed Hodge theory. So if I look at the singular cohomology of this affine variety, in particular, well, okay, it has a mixed Hodge structure. But in particular, that means it carries an increasing filtration called the weight filtration. This is defined by Deligne in the 70s. And this is an increasing filtration that starts in, well, if I'm doing cohomology in degree j, the weight filtration will start at weight j, and then increase until I stop at weight 2j. Now, in general, it's a little hard to define. The way you should think about this lowest piece is that these are the cohomology classes on this open variety that extend to some compactification, some smooth compactification. But in general, the other pieces are a little hard to get your hands on in general. However, in the specific case of the character variety, the weights, or at least their graded pieces, have another interpretation, which I want to explain. So in this case, a result of Hausel, Rodriguez, Villegas, and Nick Katz show the following, which is that they relate this weight filtration to counting points on the character variety. So I won't write this down, but the character variety, I gave you the equations for it, and they were defined over some ring of integers as long as I have that root of unity. And so if I count points on the character variety over a finite field, well, first of all, this is a polynomial function of q. Let's call it f of q. And what are the coefficients of this polynomial? Well, they exactly come for the dimensions of the graded pieces of the weight filtration. So more precisely, if I take q to the dimension hold on a second. I have to switch from Q to Q inverse because I'm not doing compactly supported cohomology. This is equal to f of Q. So in other words, in this case, the dimensions of the graded pieces with respect to the weight filtration exactly tell me about just counting points on this character variety over finite fields. And so that's another interpretation of what this weight filtration is telling us. It's giving us some kind of arithmetic content about this character variety. Oh, the star is, I'm summing over, I'm ignoring the cohomological degree. So I'm taking the Euler characteristic with respect to that. So this is summing over star and J. Yeah, thank you. Okay. All right, so this is some structure now defined on the right-hand side of this equality, this weight filtration. And it's something that depends, the way this filtration is defined, it depends on the structure of this character variety as an algebraic variety. And so the question then, this kind of vague question, is what meaning does this have? What meaning does this weight filtration have? So this is defined with respect to the character variety. What does it mean on the other side? Okay, the way I've written it is actually a yes or no question. And this would not be a very interesting talk if the answer were no. So in fact, I'll say the answer to this question is yes. Let me tell you what it is. Well, first, maybe before I do that, let me tell you what it isn't. So you could ask, maybe the first guess would be that maybe it just corresponds to the weight filtration on the other side. Okay. So first, this is not the weight filtration on the Higgs moduli space. Because it turns out the weight filtration on the Higgs moduli space is what's called pure. It only lives in that lowest piece. So the weight filtration on the Higgs moduli space is not so interesting. The weight filtration on the character variety is very complicated. So instead, the answer, which was proposed by De Cataldo, Housel, and Migliorini around 2010, is to study instead what's called the perverse filtration. Which has to do with the topology of that Hitchin map that I defined before. So recall, if I have this Higgs moduli space, it has a structure of a Lagrangian fibration over some affine space of half dimension. And the topology of this fibration you can use to define a filtration on the cohomology of the Higgs moduli space. And I'll give two definitions of it. So first of all, what I want to say is this pi defines a filtration on the cohomology of the Higgs moduli space. So I'll give two ways of thinking about this. First, let me give the original definition, which is not so illuminating, and then I'll give a more topological way of thinking about it. So the original definition is what I'm going to do is I'm going to take the constant sheaf, so with respect to the analytic topology, and I'm going to push it forward to my base. So this is going to happen inside of the constructible derived category of sheaves on affine space. And so using what's called the decomposition theorem, this derived push forward splits as a direct sum of shifted perverse sheaves. So I won't define perverse sheaves, but the way I want you to think about this is that if this map were just a smooth map in addition to being projective, then each of these perverse sheaves would actually just be a shifted local system corresponding to the cohomology of degree A of the fibers. So over the smooth locus, this PA is basically the local system cohomology. But then as the fibers become more and more singular, whatever this object is becomes more and more complicated. And then how do we define a filtration using this? Well, I'm just going to define a filtration by taking the first, however many summands of this direct sum and taking their contribution to the cohomology. So the kth piece of the perverse filtration is just going to be the cohomology of just instead of taking the whole summation, I'm just going to take the first k plus 1 pieces. If this were a smooth map, this would be normally what we would call the Leray filtration. But because it's not a smooth map, I have to kind of throw the word perverse on top of it. It's because PA is not, this is not actually a local system, it's shifted by D, so then I just want to shift it back. No, the idea is that local systems are not perverse sheaves, you have to shift them by D. So I'm just kind of compensating for that. Okay. All right, so this is the definition. It's very hard to think about, at least for me. So let me give you another way of thinking about it, which is due to Di Cataldo and Miglerini. From 2008, which says the following. So again, I take my Hitchin map from the Higgs moduli space to affine space. And then inside of this affine space, I'm going to take kind of a descending flag of affine subspaces. So let's say this is codimension 1, so D minus 1, D minus 2, and so on. Okay. And these are always kind of generically chosen. And then I can take their preimage upstairs. So this is contained in pi inverse of lambda d minus 1, pi inverse of lambda d minus 2, and so on. And so another way of thinking about this perverse filtration is as the kernel of various restriction maps to these subvarieties. Okay, so this is equal to the kernel of the restriction map, the cohomology of M Higgs to the cohomology of one of these preimages. So what is this saying? So, for instance, if this family were just a trivial family, then all of these restriction maps would be kind of an isomorphism, except for the very last one, which is just the zero map. And so in that case, this perverse filtration is just zero until you reach k equal to star, in which case it's everything. But once you start picking up some singular fibers, then these kernels become more and more interesting, and you get a more interesting filtration. And so I want you to think about this kind of verse filtration as measuring as some measure of the complexity of the singularities of this map. Okay. So do I have time? I have 15 minutes? No. 25 minutes. Okay. Oh, great. Okay. So let's just do it before I state the conjecture, which I think you can guess what it is. Let me just do an example, a couple of examples of what this perverse filtration looks like using this definition, which is a lot easier to kind of work with. Okay, so the first example is one I just kind of said out loud, which is this case of r equals 1. So in that case, as you might remember, the Higgs moduli space is just degree D line bundles cross affine space. And the Hitchin map is just projection onto the second factor. So it is one of these, it's basically a trivial fibration in that case. And so just by tracing through these definitions, you see that P, the kth piece of the perverse filtration is equal to 0 if k is less than j, and is equal to everything if k is equal to j. Let's do a more interesting example. So I'm going to take, this comes from a certain rank 2 family, but I'll just tell you what the geometry looks like. I'm going to take an elliptic curve cross A1 and mod out by the action of plus or minus 1 on both factors. This gives me some double point singularities, which I can then resolve. And then it has a projection to A1, which is just mapping onto the second factor. So A1 mod plus or minus 1 is just A1. And so this is what the Hitchin map is going to be in this case. And concretely, what this looks like is that this is going to be an elliptic surface over A1, where all the fibers are kind of, the same, except for the central fiber, which looks like this. So what does the cohomology of this look like? So the cohomology of this space, because there's just one singular fiber, I can just deformation retract everything onto that central fiber. So in H0, I get something one-dimensional. H1, I get something zero-dimensional. And H2, I get something five-dimensional. Okay. But now if I study what happens to the perverse filtration, using that definition that I just erased, what you see is that, okay, this class has perversity 0. But these 5 classes, 4 of them, end up in perversity 1, because these are the 4 classes. These 4 lines, vanish when I restrict to a generic fiber. So this q to the 5 splits into a q to the 4 here and a q here. And one thing I want you to notice is that, before, if I just looked at the cohomology, I didn't have any kind of Poincare duality symmetry. But once I kind of just only paid attention to the perversities, it's kind of restored. I get something palindromic. And that's a general feature of how the kind of perverse filtration is defined. Okay. So now I can state the conjecture. Which says that, okay, so again, non-abelian Hodge theory gives me this identification of cohomology between the cohomology of the Higgs moduli space and the cohomology of the character variety. Inside of here, the left-hand side, I have this perverse filtration. Over here on the right-hand side, I have this weight filtration, which I'm going to double the index. And the conjecture that they made in 2010 was that these get exactly identified under this non-abelian Hodge correspondence. And it turns out, this is not hard to see, is that actually the weights here only jump in even degrees. So this W2K is the same as W2K plus 1. So in other words, you can kind of nail down exactly what the weight filtration looks like using the topology of the Hitchin map. All right, so let me kind of spell out what that looks like in terms of these two examples. Okay. Now, I don't know where to erase. I'll just erase, because I want to keep those examples up. Let me erase here. So for instance, in this first example, I explained kind of what the perversities looked like on the Higgs moduli space. Where basically it's kind of trivial. It only jumps at one spot. Similarly, on the character variety side, I'm looking at the cohomology of C star to the 2G. And it's not hard to see, using just the Kunith formula and just using what we know about C star, that this will kind of only jump when the weight is equal to twice the cohomological degree. And again, that just follows from a calculation for C star itself, where in degree 1, that class has weight 2. This example is more interesting. I didn't really tell you what this is as a moduli space of Higgs bundles. It turns out it's related to not a P1 with some kind of orbifold structure. But I'll just tell you what the character variety looks like. Which it looks like I take a cubic surface inside of P3. And then I take the complement of a kind of triangle of lines. So this is the character variety side. And okay, well, I won't do the calculation, but you can at least do the point count to see what the dimensions of the weight pieces are. And so if I do the point count, I get 1 plus 4q plus q squared. Yeah, this is really like rank 2 with like maybe parabolic or something. Yeah. And so, well, okay, this would have been more convincing if I hadn't erased the perverse calculation, but this 1, 4, 1 is exactly what I saw on the other side. Okay, so this matches. At least numerically it matches with this kind of q to the 4q. So let me say now what we know and some of the background. Actually, before I do that, let me just say why this conjecture is maybe interesting. So first of all, where did it come from? Why did they propose this conjecture? Well, the idea was that Hausel and his Rodriguez-Villegas, who I mentioned before, had done a lot of calculations of these kinds of point counts on the character variety side, and noticed that they were always getting this kind of palindromic symmetry. On the other hand, that kind of symmetry is automatic from the point of view of this perverse filtration on the Higgs side. And so basically, this conjecture was proposed as a way of explaining that. And so more generally, one reason why this conjecture is interesting is that it kind of has interesting implications in each direction. So why is it interesting? It has kind of non-trivial constraints in each direction. So for instance, this is what I just said, this perverse filtration, because of how it's defined using perverse sheaves, always has this kind of, palindromic kind of hard Lefschetz structure. And so it implies that if I look at the associated graded with respect to the weight filtration of the cohomology of the character variety, satisfies a version of kind of the hard Lefschetz theorem. It's kind of a surprising version of it because this is now some non-compact variety, so it's not going to be anything like the usual version of hard Lefschetz. And this is why it's usually called the curious hard Lefschetz. And it turns out later on, this kind of property was proven directly. So this was proven directly by Mellet, Anton, in maybe 2019, something like that. In the other direction, the weight filtration, because of how kind of naturally it's defined, is compatible with cup product. So in the other direction, for instance, implies that the perverse filtration and that's something that's very non-obvious. It's not always true. So this is something this is usually not true. If I give you some random, proper fibration, the perverse filtration usually will not behave well with respect to multiplication. So it's something special about this Hitchin man. Maybe let me mention, since Yukonobu is here, another interesting consequence of the P equals W conjecture, which is how I got interested in it, is that this implies a conjecture we made from 2016 regarding curve counting on Calabi-Yau threefolds in the special case when the Calabi-Yau threefold is the total space of the canonical bundle plus the structure sheaf. I won't go into this. Hopefully, if you were at his talk, then maybe you heard about this. But the point is that what this conjecture said was that if I look at your favorite curve counting theory on X, Gromov-Witten theory, DT theory, whatever, it should be equivalent to some kind of Euler characteristics of some perverse sheaves on some other moduli space associated to X. In this special case, using the P equals W conjecture, you can read that off from some appropriate point counting. So this ends up relating, let's say, the Gromov-Witten theory of X to some kind of point counts on one of these character varieties. And both of these have been worked out, a long time ago, so you can just check they match. Okay. So now let me say a little bit about what we know. So the history. So when they proposed this conjecture, 2010, they didn't just propose it, they also proved it in a highly non-trivial case. They showed it when the rank is 2 and genus is arbitrary. That's a real kind of, it's an intricate argument, but it's kind of very convincing, I think. Then Mark, myself, and Jun Liang, many years later, showed it in kind of the other extreme example, which is all rank, but only genus 2. So kind of the other extreme. And then finally, now we have kind of 3 proofs of this conjecture in general. So myself and Jun Liang, Housel, Manetz, Mallet, and Schiffman. From 2022, and then there was another proof found by myself, Jun Liang, and Qizhang Yin the next year. Okay. And this is kind of the general case, all G, all rank. Sorry, how much time do I have left? 5 minutes? Okay, great. Let me just say what we don't know. about this conjecture. So the original conjecture, I guess, has been proven. But there's a lot we don't understand. Well, first is at the very beginning of this talk, I kind of put myself in the coprime situation. But you could try to work in the non-coprime case. Now the moduli spaces are singular. And then you can try to kind of study things there, either using, for instance, intersection cohomology, or work with something like the homology of the stack. Okay, there are formulations in both settings, and they're kind of known to be equivalent to each other, but neither one is known. The second thing we don't really understand is the case of other groups. So I kind of focused everywhere on the case of GLN. But non-abelian Hodge theory is something you can talk about for arbitrary reductive groups. And this conjecture, the analogous conjecture can be formulated, but it's, I think, wide open. And for instance, we still don't know how to do it in the case of SLR. So still in type A. And then finally, and I think most kind of relevant, is the way I've kind of phrased this as conjecture about kind of, these moduli spaces that show up in non-abelian Hodge theory. But I think the feeling of everyone who's thought about it is that this is somehow just an artifact of how we kind of discovered this phenomenon. And that there should be kind of some much more general version of this correspondence that happens in kind of varieties that have nothing to do with, Higgs bundles on a curve or anything like that. And so, for instance, there's work of, let's say, Zili Zhang on cluster varieties, and so on. I think what we're missing right now is exactly what are the right adjectives you need to put in order for something like this to be true. Okay. So in just a few minutes I have left, let me just say a little bit about what kind of goes into these arguments. In particular, maybe I'll kind of focus on this first one because that's the one kind of I'm here for. And so what all of these proofs have in common is to really focus on the perverse filtration side, on the Higgs moduli space side, and try to understand some of these surprising properties about it. For instance, I said before that one kind of surprising implication of the conjecture is that it's compatible with cup product. And so basically one thing that has to go on is you try to have to kind of understand those properties directly. And I give two definitions of the perverse filtration. And those definitions have many redeeming qualities, but they're just not good for the kind of fine analyses you need to prove this conjecture. So all three of the arguments use some kind of extra symmetries in the problem to help control this perverse filtration better. So the idea is to use some kind of extra symmetries. So for instance, in this first proof, the idea is to exploit what's called a global Springer theory, which was developed by Ngo and Zhuai Yun, I don't know, a long time ago, let's say 2008. In this proof of Hausel, Mellet, Minetz, and Schiffman, they use the structure of what's called a cohomological Hall algebra, which is some kind of, Hecke-type algebra, which they show acts more or less on the cohomology of these moduli spaces, and they use that to kind of find some extra symmetries. And then finally, this last proof is less representation theoretic, and the idea is to instead use some kind of, partially defined Fourier-Mukai transform. So some symmetry of the derived category, and use that to help understand the perverse filtration. Okay, let me stop here. Thank you.
Questions?
Okay, thanks. I would like to ask, do you have any comments on the P equal to W conjecture on wild character varieties?
No, no, that's another open. Interesting, but I don't have any. I mean, a lot of the steps that we use, some of them will apply in that setting, but a lot of them break down. So I don't think a lot of the arguments we have don't apply in that setting right now, I think.
But is there any evidence that this will still will hold?
Oh yeah, I think that's a situation where I think people believe it quite strongly. There's a lot of numerical evidence, for instance, in that case. So I think that's a situation where we're very confident about it. I mean, I think anything that's kind of within sniffing distance of non-abelian Hodge theory, I think basically everyone believes all those kinds of extensions of the conjecture, even though whether or not we're close to proving it or not. It's more the situation where you leave that world where I think maybe opinion is less clear.
Okay, I see. Thank you.
Thank you.
More questions?
Oh, yeah, Mark.
Wait.
Oh, thank you. Thank you. Oh, okay. Seems like going from GLN to SLN would not be much of a stretch. What's the problem?
It's so annoying. Yeah, so the idea is that one of the things that we use in this argument, which I did not talk about, is that we know we have a lot of information just about the cohomology ring on either side. I mean, they have the same cohomology ring. And we know, for instance, how they're generated. So in the case of GLN, the moduli space of Higgs bundles is generated by just tautological classes. So things you get from the universal Chern class of the universal bundle, you take like Kunis components. And we know that those classes don't generate the SL moduli space because they lie, I mean, there's some finite group action, they all lie inside of the invariant part. And so what we need is we just need some way of accessing the other parts of the cohomology that you can't see in a way that makes sense on both sides of the correspondence.
But you know how to compute it, you just don't know how to relate it on both sides.
Yeah, that's right. So on the Higgs moduli space side, the other pieces of the cohomology can be understood using what's called endoscopic correspondences, so using some lower rank moduli spaces of Higgs bundles. But it's not known that approach, it's not known, I just don't know how to do that on the other side in a way that's compatible.
On the wave side, the wave filtration canonical split, can you see that from the perverse side? Is that corresponding to something?
So, yeah, that's a good question. So the question was about, there's a canonical splitting on the weight filtration side. So on the Higgs moduli space side, I mean, there are, in general, if I give you a proper map, this sounds dumb. There are four, if I pick an ample line bundle, there are 4 canonical splittings, which seems to be the same as saying there are no canonical splittings. But nevertheless, there are kind of 4 a priori different ways of canonically splitting the perverse illustration once I make the choice of a relatively ample bundle. And so I think, do I know that? I don't think I know this, but the expectation is that in this case, those 4 choices all agree and then should agree on the other side. But I don't know of a direct way of seeing any of those statements. For instance, that grading on the weight filtration side, it's a splitting that's compatible with the cup product. So the analogous statement on the left-hand side, I do not know how to prove. Is that true? Not without kind of going to the other side. I don't know how to see that directly.
More questions? So one quick question. Can you say again, so in this local curve Calabi-Yau threefold, what kind of sheets you're counting compactly supported sheets? Like curves set theoretically supported on a curve?
Yeah, that's right. I mean,
and what?
So I'm doing like, let's say I'm doing on like the DT side or whatever. So I'm counting, sub-schemes that are kind of are proper inside of this non-compact Calabi-Yau threefold. And if I'm doing on the DT side, I can just think of them taking like some weighted Euler characteristic of that moduli space. Yeah. And so then the conjecture is that generating function, whichever one you want to pick, can be read off from, in general, you take the moduli space of like one-dimensional sheaves on the Calabi-Yau threefold, and then kind of study the Hilbert-Chow morphism and play around with that.
I see.
And so, I mean, you weren't able to go to Yokonobu's talk because you were here, but that's some 2-cent summary of the conjecture in Yokonobu's case. And then in the specific case of that specific Calabi-Yau threefold that I wrote down, if you unwind both sides, on the kind of DT side, that's just a calculation that was done from the old days, and you get an answer. On the other hand, you can do the answer with the perverse filtration, turn it into the weight filtration, and then you get this point count that was done also 20 years ago, and they just match up.
Okay. More questions? If not, let's thank Davesh again.